Hello and welcome to my book club. This month we read Gödel, Escher, Bach by Douglas Hofstadter. Now this book is not the easiest book to read. It's over 750 pages when you include the notes and annotations in the end. And it's about a difficult topic. It's something that even me, having learned about a lot of these ideas in other classes and other places before, there were some sections that I had to stop and pause and reread it to make sure I understood. And it's not because Douglas Hofstadter is bad at explaining things. It's not because he's not a sophisticated and eloquent writer. The difficulty is the ideas themselves. However, I think that these ideas are very important. And I think there's some of the most interesting ideas that I've ever read about. Now, what is the idea of the book? Well, at the core of this book is the idea of a strange loop, or what Douglas Hofstadter calls a strange loop. So what is a strange loop? Well, I think it's easiest to visually represent what a strange loop is if we look at the second person in the Gödel, Escher, Bach trilogy here of names, MC Escher. MC Escher was an artist who was famous for doing mind-bending, paradoxical kinds of images where one setting, which appears to be the foreground, turns into the background, or something that is the subject becomes the object. So some of the classic ones that you probably have seen before of his is the staircase that continually goes upwards. So it's a two-dimensional picture, but it shows a paradox. It shows something that couldn't exist in the physical world. Another example is the drawing hands, where he has drawn two pictures of hands which are holding pencils and they are drawing themselves. Other ones he has include birds which turn into other animals and shift between the foreground and background. He even has one where there's a person looking at a picture in a museum and the scene is warping so that he is actually part of the museum, part of the picture itself. So this is something that I think is easy to see visually, this kind of paradox. And it is easy to dismiss it as well as just being a little bit of trickery. You might not even be a big fan of MC Escher's art. You might consider it a little bit too obvious. Perhaps you see it and you're like, oh yeah, he's trying to do some kind of visual illusion, tricking us because it's really a two-dimensional picture and we're operating with our three-dimensional brains trying to impress rules upon it which don't really apply. However, I think it's a really good entry point to grasping this idea of a strange loop. Now, what Douglas Hofstadter calls a strange loop, or this tangled hierarchy, is where you have layers of something where something is built on top of something else. So we can all think about this in, for instance, in the physical world. We know that the world is made of atoms and quarks and basic elementary particles, but then on top of that level we have chemistry, and chemistry is a greater abstraction, something built on top of physics. On top of chemistry we have, let's say, biology, and on top of that psychology, and then sociology, and etc., etc., etc. So this is a hierarchy, and what a strange loop is where this hierarchy flips back in on itself. It's where the top layer somehow also becomes the bottom layer. So this is where the MC Escher idea comes up of the staircases that just go up and up and up, but they somehow end at the same starting point. Now, I have to admit, Johann Sebastian Bach was not someone that I knew a lot about his music prior to this. I'm much less well-versed on music than Douglas Hofstadter was, so I'm just going to take his word for it that a lot of the musical conventions that Bach used had this similar quality of fugues, of ideas that are repeating and turning on each other and having the same kind of self-referential, paradoxical sort of quality, but in a musical domain, as opposed to MC Escher, who's an artistic domain. Now, what about the first name in this book? Gödel. Now, really, it's called Gödel, Escher, Bach, but those names don't have equal weight. In this book, it is mostly about the mathematician Kurt Gödel, or the logician Kurt Gödel. Now, he has one of the most amazing discoveries in mathematics, in logic, in just the ability to reason I think I've ever heard. And I think it's worth studying. It's worth studying in and of itself because the idea it presents is so mind-boggling and it's difficult to really fathom the implications of. But also because the way he did it is a perfect example of this strange loop. It's a perfect example of this MC Escher idea of one idea being built on top of each other. Now, the difference between MC Escher and Gödel is that MC Escher is kind of doing a bit of a trick. He's drawing a situation which can't possibly exist, but we're easy to dismiss it because we know that, well, it's just really a two-dimensional picture. It doesn't have to represent something that's physically realizable. Whereas Gödel, I think his trick was much more impressive because he's doing it within the field of mathematics and logic itself. So he's doing this bending, twisting hierarchy of one lower level being built on top and top and top of each other until it comes down and reaches to the bottom level again. Within the realm of logic, something that you would think would escape the ideas of paradox, would escape the ideas of this self-referentiality, which is the work we can find in Escher and Bach. Now, why is this important? So before I go into Gödel's actual proof and explaining why it's so mind-bending and why, honestly, it's one of the most interesting things that I've ever learned, before I want to go into that, I want to talk about what the implication is, because at the end of the day, this might be interesting, but maybe not enough for you to wade through 750 pages of a book to talk about some esoteric idea of strange loops. Well, the basic idea of where this is going is that Douglas Hofstadter believes that this is a very potent tool, a very potent idea that we can apply to human consciousness itself. So what are we actually? Is, in Hofstadter's mind, a strange loop? Is a situation where the hierarchies that we're built upon flip back down onto themselves. Now, that may sound confusing, and I hope as I explain the nature of the proof, how it was done, and then later draw links to human consciousness, it will make a bit more sense. It is a little bit of an abstract idea. It's a little bit hard to wrap your mind around. As I said, it's a 750-page book. Not only did I read all of it, but I had to reread some of the parts, especially when they're talking about Gödel's proof and how it was executed technically, because it's very difficult to wrap your head around. So if you're listening to this podcast and you hear it the first time and you're like, you know what, I didn't get any of that at all, that's okay. But keep in mind, I want you to just keep a kernel. Even if what I'm saying sounds a little weird or you don't get it, keep it in mind because you might want to come back to it. You might want to come back a few years later, a few months later, look at it again, maybe read this book, Gödel, Escher, Bach. Maybe you will watch a documentary about Gödel. There's a really good one. You can read books about it. Essentially, I think that if you spend a little bit of time with this idea, maybe over a couple of years, it will really strike you as profound. It'll strike you as something that I think upheaves a lot of our ideas about how the world works, about who we are, and how we can be related to something which seems so alien to us, in the sense that when we imagine the world, when we're living in it, our sense of consciousness seems so divorced, so alien from the quantum mechanical rules that physicists discover, or the mechanical ideas of chemistry and molecular biology. How can we be related to that? And I think there's a real profundity to this. In addition, I think this is an idea that is one of those analogies that if you really get it, applies to many, many places. It certainly applies to human minds, but it also applies to DNA, as we were talking about in the book, the very machinery that makes us alive. This is an idea that underpins it. Computers is a huge idea. I know that many people, after reading this book, decided to study computer science because they thought it was so fascinating, this sort of idea of a tangled hierarchy or a strange loop. So I'm going to start explaining the idea, but I just want you to keep this in mind because it may sound a little over your head or too esoteric, or who cares about mathematical logic. But I think if you invest in it, if you put the effort to try to get to the other end of the idea, you'll really see it has pretty broad implications. So let's get started. Gödel's famous idea is comes together in what is known as his incompleteness proof. And to understand this, you have to understand the setting at the time. So it's just the beginning of the 20th century, and there are a number of unsolved, outstanding problems in mathematics. The mathematician David Hilbert even formulated a lot of these problems as a to-do list for mathematicians to solve. And one of them was to prove the consistency and completeness of axiomatized mathematics. So what does that mean? What on earth does that mean? Well, we can think about it this way. In mathematical reasoning, we all have some informal idea of what it means to prove something. Maybe you even in a mathematics class seen a proof of Pythagoras' theorem where a squared plus b squared equals c squared for the lengths of sides of a right-angled triangle. You could maybe have gone through a mathematical calculation of that, or maybe you've even seen one of those visual intuitions where they put the squares with the grids on the sides of each of the triangles and they just happen to add up. Now, we can understand this intuitive level of a proof, but there was always a little bit of a worry that perhaps we're making a mistake. How do you know that you've really proved something? Maybe you've convinced yourself, but there's a little secret glitch that undermines a lot of your reasoning. So one of the efforts to really make this more rigorous was to axiomatize mathematics, which was to basically turn this process of coming up with elegant and intuitive proofs into something that was completely mechanical, something a computer could do, and assuming you didn't write any bugs into the program, it would only return correct answers. So the basic idea is that you have a formal system where you have some axioms. These are things that you take for granted as being true. Now, it may sound like it's a bit of a problematic, how do you know what the axioms are? But really think of the axioms as the things that characterize what you're wanting to discuss. So if you wanted to discuss geometry, you would come up with different axioms than if you wanted to discuss number theory or something else. Basically, the axioms are going to tell you what areas of mathematics, broadly conceived, you can explore. All right, so you come up with some list of axioms. Hopefully it's a small list of axioms, or if there are a large number of axioms, they can be represented by a rule for creating those axioms. Next, you want to come up with some rules for manipulating these symbols. So you write out the axioms as a list of symbols, just like you would in a computer program. And then you come up with straightforward rules that if you apply it to an axiom, you get something that's true at the end. So again, this may sound a little complicated, but really we do this all the time. If you've ever studied algebra, you know about, well, if you have multiply by 2 on one side, you can divide both sides by 2, eliminate it on one side, and then have divided by 2 or multiply by 1/2 on the other. This is pretty basic. This is something that we learn in, grade 7 or 8. Now, this algebraic manipulation is very similar to what's happening with axioms and theorems. Basically, what we're doing is we're starting with the axioms, our 1 + 1 = 2 or similar types of propositions, and we're manipulating them in a way so that we can get other true statements of arithmetic. So if we follow these rules, eventually perhaps we can reach 2 + 2 = 4, for example. Now, this is a purely mechanical process. I can't stress this enough. This isn't the case that what was happening here is we're discovering the truth of mathematics. No, what's happening is we're taking these axioms, we're taking these basic rules, and we're just following very mechanical procedures to turn them into other statements, which we hope, if the system is designed properly, will give us the true statements of mathematics. So what was Hilbert's problem? Well, Hilbert's problem was that there were known different axiomatic systems for mathematics. In particular, a later one that was developed, which was the subject of Gödel's proof, was Principia Mathematica, which was a really exhaustive attempt to really underpin all the foundations of mathematics, to really codify, as if it were, of what it was. Now, this essential idea is that you're going to take these axioms and you're going to manipulate them with these mechanical rules. What we would like to know are two things about this system. First, is it consistent? And what I mean by consistent is, does it ever derive a contradiction? Now, because we're not talking about quote-unquote real math, we're talking about a mechanical system that's following mechanical rules, there's always the chance that you could have written a rule incorrectly. And your rule, if you follow it in some weird case, might lead to a situation where you get 2 + 2 = 4 if you follow a certain set of combinations, and it gets 2 + 2 = 5 if you follow a different set of combinations. Or it gets 2 + 2 doesn't equal 4. So this is a situation that we want to avoid, obviously, because if we want our mechanical system to represent truth in mathematics, to find the answers of what are actual real formulas in mathematics, this is something we want to avoid. Now, there's another thing that we would like to do with this system. Now, it's possible to make a consistent system that nonetheless misses important rules. It doesn't allow things that we consider are important in order to get true statements. So if it's too underpowered, if it, let's say, lacks the ability to represent multiplication, then there's going to be a whole set of facts about numbers that we all admit are true that are completely outside the realm of this ability to solve them. So we're going to have a huge set of ideas that we accept are true but are nonetheless unprovable within this formal system. So Hilbert's real idea was, if someone could come up with a proof that shows that arithmetic under one of these axiomatic systems was consistent and also complete, that would be a major triumph. We could feel very secure resting in our knowledge that this mechanical system we had would work all the time. And what Gödel did in the 1930s was he showed that this was actually impossible. That any system that you have, any set of rules that you have that is powerful enough to represent the basics of natural numbers, the basics of arithmetic, will ultimately undermine itself by creating situations that we know are true but cannot be represented in it. So this is a real fascinating result. Like, well, what does this mean? And so I think we can go through the proof now and understand a little bit of how it works. Now, I'm going to be glossing over a lot of details. Douglas Hofstadter goes through a lot of these details in painstaking effort, so you can see from start to finish the entirety of the proof. And I think there's merit in that. I know that this book is quite long and you might be somewhat reluctant to push your way through it, but I think there's merit in fully understanding the proof, because whenever someone presents you with a really mind-bending idea, if you don't fully understand it, it's very easy to dismiss it on some ground that isn't actually valid if you really understood it. So I think that can be the case here, that in my cursory overview, you might think, oh, well, what about this or what about that? I just want to caution you, even if I'm not the best at explaining this idea, even if I skip a lot of parts, the whataboutism is probably not going to work here. There's not going to be a situation where you're going to say, well, what about this? And it's really going to undermine the idea of the proof. It is really that ironclad. However, in order to see why it's ironclad, you have to go through a lot of pages of how the proof actually works. So this is going to be a summary version, but I'm just asking you to just be careful with your objections if you see some sort of problem with this idea. So here's the basic idea of the proof. And this is really Gödel's major trick, because this is the strange loop. This is where Douglas Hofstadter decided to pin this in his book idea as something so profound and reaching far beyond mathematics. Here is the idea. We take the formulas in this system. So we take the formulas that say, all the little symbols that make these things, and we represent them in a code, just the way that we would in a computer program. We make them into a code in actual numbers. Now, these numbers, the rules of operating on these axioms to get new true statements, to get new theorems of this arithmetic system, the way of doing this, operating on this, can get us a mirror version of this system in mathematics itself. So you could imagine, like I was saying with algebra, this divide on one hand and divide on the other hand as let's say a rule of algebra, that if you have something that's multiplied by everything, you divide everything on one side, divide everything on the other side, the equality still holds. Well, what you could imagine doing is taking that rule of having this sort of progression of timesing this, multiplying by this, and representing it as an actual statement about numbers. So you have actual numbers representing the dividing sign, And then these relationships between these things, the relationship between the statement before you divide it by 2 and after you divide it by 2, isn't just a progression in the numbers, in the actual symbols of mathematics. It is an actual arithmetic transformation of one number into another number. And this means that we can, within the system itself, ask questions about these numbers, the same way that we can ask questions about prime numbers, let's say in number theory, or we can ask questions about which numbers are powers of 2. We can also ask questions and say, hey, is this number to this number a valid transformation within this existing system? Now, the exact way of coding that up is going to be a little bit complicated, and this is part of the proof that required a lot of work and a lot of thinking, but I want you to leave the essential insight here, which is that the actual system we're dealing with here is a bunch of symbols that use numbers, and what he is doing is turning those symbols into numbers within the system. So you can think of a normal statement of 2 plus 2 equals 4. So you have a 2, you have a plus sign, you have a 2, you have an equal sign, you have a 4. What Gödel is doing is saying, let's take that 2, let's put it into a number. Let's take that plus sign, let's put it into a number. Let's take that 2, we'll put it into a number. Let's put that equal sign, we'll put it into a number. Let's take that 4, we'll put it into a number. And then we have one super long number that represents 2 plus 2 equals 4 as just a number, not as something that involves plus signs and equal signs and has separate numbers, but just one big number. Okay, so what can you do with this? Well, if you go through a little bit of work, what you can end up doing with this process is you can make a statement that is the mathematical equivalent of saying this statement is false. Or more specifically, what it's saying is this statement has no proof. Because you're representing the numbers within themselves, you can have a statement that refers to its own number. So you can make a proof that says there is no proof for this particular statement. Now, what does that mean? Well, it's interesting. It's not saying that this statement is false. Let's be clear about that. It's not saying that, hey, this statement we have here is false. It's saying that it can't be proven. And what that means is that a statement that says, essentially, this statement has no proof, well, if this statement is saying it has no proof, then that means that if it's true, then it doesn't have a proof. Or if it's false, then it means that there is a contradiction here. So you can see, if we go back to Hilbert's problem of consistency and completeness, that this is now impossible. Because you have a statement that it gives you a forking path. On the one hand, you choose inconsistency. You choose a statement that it's false and we know it to be true. Okay, how do we deal with that? The other statement is that if, let's say, we take it to be true. Let's say we say that this is a true statement. Well, now we know, because it's a true statement, that it doesn't have a proof. And because it doesn't have a proof, we know that there are results in mathematics that are going to be forever outside our reach, forever outside the realm of our logic to reach. Now, there's a lot of profound ideas in logic and mathematics because of this. There's also a lot of related proofs. For instance, a somewhat more comprehensible, but I think a little bit less elegant idea is Alan Turing's halting problem from computer science. Basically, this says that it's impossible to write a computer program that can analyze other computer programs and say for sure whether they stop. It's also related to Cantor's diagonal argument, which is the idea that if you make a list of all the real numbers meaning numbers that have decimal and whatever numbers after that it's impossible to list them all out, because no matter how many you put on a list, it's always possible to create a new number that's not on your list. So all of these cases, I think, hint at some limits of the ability to reason within these systems. They show that it's impossible to avoid paradox. It's impossible to make a situation where you have complete rational control over the universe. So that's one of, I think, the really profound ideas. But if we follow Gödel, Escher, Bach, this book, that isn't really the crux of what Douglas Hofstadter is trying to argue here. That isn't really why he brought up this proof and why he devoted hundreds of pages to explaining it. Instead, what he wanted to talk about were two things. First, the idea of formal systems. The idea of a system that just mechanically following rules and then building something more complicated out of that. This is the basis behind computers, yes, but it's also the basis behind the physical world. It's the basis behind objects that interact via basic, simple physical laws. It's the basis of how DNA combines and replicates, all the machinery in our cells. So there's something worth studying just in the idea of a formal system itself. The second idea is that of the strange loop, the insight that Gödel had, which was to represent the rules of the system within the system itself. This kind of inception-like idea of taking a system and mirroring it within the system itself. Now that might sound impossible, but as again we saw, Gödel was able to do this. And if you follow the proof to its end, you can see that it logically follows. It doesn't involve some kind of contradiction. It doesn't involve magic. It's just a simple fact that when a system becomes sufficiently powerful, it can eventually represent itself or a version of itself within it. So what does that mean? Well, what I think that means here is, first of all, understanding things in terms of formal systems is a very potent idea. Being able to think about things in terms of following ironclad laws or rules is very powerful. But then the second idea is that once we reach a sufficient representational complexity, we can have this ability potentially to loop back on itself, to contain it. So what's the extension here? Well, one of them is the idea of human consciousness. So what is he saying about human consciousness? Well, he's saying that what perhaps the self is, what we are, as not bodies, but just sort of as some kind of abstract quality, what makes us different from rocks or perhaps computer programs that we have today, is that our machinery for representing things in the world is sufficiently complex that we can represent ourselves in that machinery, and we can represent ourselves representing ourselves, that we can have thoughts about our own thoughts, about the person thinking the thoughts, and about their relation to the world at large. That this kind of turning back on itself of the thought machinery within the head is very potent, and that this can happen within a system which nonetheless is just obeying sort of mindless rules and mechanical properties. Another idea that comes up here, and this is a philosophical concept, but is the idea of the difference between syntax and semantics. So what is syntax? Syntax is the rules and mechanical structures of usually sentences in language, but it can apply more broadly. And semantics is what those sentences, what those words mean. And what Gödel showed is that this boundary between syntax and semantics is not cleanly dividing. It's not the case that there's just syntax on one end of mechanical rules and then the meaning is completely cut off from it. And the reason that we know this is because Gödel's own proof was done within a system that is completely mechanical, that is entirely syntactical. It is not necessary for you to, any interpretation you make on these rules saying that they correspond to real statements in arithmetic or real statements in number theory, is just your interpretation. What you say they mean is what you're applying on top of it. It's just a mechanical system. And yet, what is happening here is that this system itself is creating its own substructures so that it can refer to itself even though it's only a syntactic system. That by setting up the equation just right, by setting up the formulas just right, you can get this system that talks about itself, that talks about the rules of itself and makes those implications, makes those inferences. So you could argue that, well, perhaps this doesn't represent genuine meaning, this doesn't represent genuine semantics in the sense that we can write out this proof, but someone still has to know what it means, someone still has to know what it is. But I think it provides an important bootstrapping. It shows how a system that is composed of just mechanical things, just meaningless symbols, can acquire meaning, and it can do that within itself. It can bootstrap itself out of there. And I think this has really profound consequences for many areas. Now, what's the implication here for artificial intelligence and those kinds of things? Well, this book was written quite a while ago, and because it's been written quite a long time ago, it was written prior to many of the more recent developments in artificial intelligence, certainly deep learning and machine learning, the things that everyone's talking about these days. So in some sense, this book is somewhat dated. When we get to the end and Hofstadter starts talking about AI, he's very much stuck in the old paradigm where humans basically thought, well, if we're going to make a computer that thinks, it's going to think kind of the way that we do higher level reasoning. It's going to think in terms of, well, here's some symbols and I'm going to manipulate them in a procedural way and get some answer. And this was sort of the dominant paradigm at the time, and it was shown through a lot of starts and failures that this was not really that workable a solution for artificial intelligence. Now, since then, we've developed much more powerful computers. We've developed processors that can go far beyond what was there when Hofstadter was writing this book. And because of this, certain algorithms that were prohibitive, that we weren't quite sure how to actually execute, we can now execute. So you have situations like AlphaZero, the new DeepMind program for playing chess, that can just operate with 5,000 specially designed hardware units to test against itself many times so that it can learn the rules of chess incredibly well. Now, this is just something that is not really programmed into the computer, so to speak, but it is something that we're developing with it. So there is some anachronisms in the later parts of the book when we're talking about artificial intelligence. However, with that in mind, I think it's still the case that we're in Hofstadter's, the same fundamental rules apply. AI has grown more sophisticated and some of the tools that we're using are different, but we're still not at a point where we would consider any of the AIs that we've seen to be conscious in the way that a human being is, and certainly not even developing the kind of self-awareness where that's even really much for debate. That's still restricted to science fiction movies and television where we have robots that wax poetically about their own humanity. Instead, we're still in an area where artificial intelligence is a fairly limited tool. But what I think Hofstadter gets right, and what is still correct today, is the future goal of artificial intelligence and how it relates to what we are as human beings and what we could possibly achieve. Namely, that if this strange loop idea is to be fully realized, is to be fully understood, then it means that creating an artificially intelligent robot that has consciousness, that has that self-awareness, that ability to think for itself and decide for itself, and is functionally similar to a human being, is at least possible in theory. Whether or not we're going to reach it, whether or not we're going to make something that is similar to ourselves or quite alien to it, whether the artificial intelligence we end up developing is going to be handicapped in some way, it's going to lack some of these qualities, is still yet to be seen. But whether it's possible in principle is still a debate amongst many philosophers. Many philosophers think that this type of artificial intelligence, this type of mechanistic reasoning, therefore resulting in some higher level semantics, higher level intelligence, higher level consciousness, is impossible. And I think if you follow the idea in Gödel, Escher, Bach, it's at least suggestive, if not a ironclad proof, that that's not the case. That we can get systems that have meaning, and the meaning is bootstrapped out of something that doesn't have meaning. That you can have a system, in Gödel's case, of just symbols being manipulated by very straightforward rules that nonetheless, if you get complicated enough, can reach back on and refer to itself. Now, one of the things that I think is interesting is that Gödel's proof is somewhat pessimistic. It's proving something about the limits of human reasoning, about our inability to find a complete and consistent set of mathematics. But one of the statements, and I'm blanking on the name of the mathematician now that was referenced in the book, but one of the statements which I think is perhaps more analogous, even if it's a derivative work and thus less brilliant than Kurt Gödel's original idea, is the idea of a very different, but very slightly different statement, which is, instead of having a statement that says that this statement cannot be proven, you just change that. You say this statement can be proven. And in this case, that actually is enough to bootstrap it to truth, that you can have something that just merely states that this statement can be proven, and without actually knowing what the proof is, you can know that that's the case. So this is something I think that's more analogous to human consciousness, that it's a little bit like a set of symbol manipulation gets sophisticated enough, robust enough, that it can say about itself these qualities that it has, and that they become kind of true by fiat. They become true sort of as an incantation, almost as a magical ritual where merely stating that this is the case becomes true. It becomes a self-fulfilling prophecy. Now, I'm not saying that if a computer were to merely output the text, I am conscious, it would become a conscious machine, but rather that the mechanism for doing so, the mechanism for underpinning our own consciousness, is very likely similar to this strange loop idea. Now, I think there's a lot of very interesting ideas in this book. It goes beyond Kurt Gödel's famous proof, although a lot of the book is devoted to really understanding it so you can get a real intuitive idea of exactly how such a feat was done. But there's also a lot of very interesting ideas about logic itself, about what constitutes knowing something. One of the interesting results discussed in the book is that as a corollary to Gödel's incompleteness proof is that it's actually not possible to say that truth, whether or not something can be true or not, can actually be represented in mathematics for a very similar reason, that you can get a situation that says this statement is false in mathematics. You can make it say that statement if you assume the idea that truth and falsity can be directly inferred from these mechanical statements. So this also points to the idea that what makes something true or false is quite elusive. It's something that it's maybe not possible for a mechanical system to fully realize truth or falsity. And just before that makes you think of a distinction between human beings and machines, I think that there's a very important section where he talks about, because of these own complications, it's not the case that human beings have some transcendental power to lift ourselves above the system, see outside of it and say, well, this system is too weak to prove it, but I can see that that's true. Because this statement is false, this statement is true, actually continues upwards, higher and higher up into the levels. So as human beings, we may be a somewhat more sophisticated system for recognizing these intuitive flaws than the computer, but because there's an infinite chain of these types of reasonings that are infinitely bifurcating until what you accept as true or false goes up and up and up and up and up, it's actually impossible for us as human beings to assess the same thing. So the implication of that, the idea that truth and falsity in this very even just mathematical sense, forget knowing about the world, forget doing scientific experiments and knowing physics, just even in logic, even in mathematics itself, we're not able to know with certainty and arrive at the certainty of truth and falsity is, I think, also quite profound. So there's many ideas of this nature. There's a huge discussion about genetics and about how molecules, again, following simple mechanical rules, bootstrap themselves into existence, how DNA replicates and then creates its own machinery for replicating itself. And it goes on and on and on. So I think there's a lot to discover in this book that I have not talked about. But I think if you are interested in this idea, if the idea of strange loops, of things that loop back on themselves, sort of paradoxical self-reference that nonetheless must be true, is interesting to you, I highly recommend reading this book. Now, it's certainly the case that this is not an easy book to read. As I said myself earlier, there were some passages that I had to reread over to make sure I understood everything. But I wouldn't say that it's an unenjoyable read. Douglas Hofstadter is an excellent writer, and he has this very unique habit of mixing topics which are about these esoteric ideas in logic and computation with dialogues, with these invented characters who themselves mirror some of the concepts, but talking about perhaps more ordinary everyday things. Additionally, because the book is somewhat about how the form or structure or syntax of things eventually becomes the meaning, I think it's quite playful the way he has put the book together, in that it involves many acts of self-reference, puns, names for things, double standing for something else. And so you can see even in the form of the book that it very much exemplifies the philosophy of the strange loop, that the form and the substance are not separable, that they can link up and mirror each other. So I think even for that, this book really, I think, is a work of art. Even if you decided after you read it that you fundamentally disagreed with his opinions on consciousness or artificial intelligence, I think you have to admire how the book was composed. And indeed, in its era, it won a Pulitzer Prize, I think, for that very reason. Now, I think this is an important book. I think this is a very interesting idea. I certainly would like to discuss more ideas related to cognitive science, philosophy of mind in this book club review. If you have any suggestions or ideas of stuff that you think that I should cover or you think that I got wrong, I'd be happy to get some emails from you and listen to your own thoughts, because this is a subject that fascinates me and I'd be happy to discuss it more. Next month, we're going to be doing the book Seeing Like a State by James C. Scott. And this is a fascinating book about the limits of organization, and indeed how many of the evolutions that we've gone through as a society and civilization perhaps were not done with the best intentions. So thank you very much for that. This was December's book, Gödel, Escher, Bach. Thank you very much.